So now let's look at an example where we're designing a circuit to meet a certain degree of stability. So let's consider this 3-pole feedback amplifier which has a loop gain function as given below. We see that the beta term has not been determined, so what we actually want to do is we want to find a value of this beta that is going to give us a phase margin of 45 degrees. And sort of as a higher level note, we say, of course, we can choose this value beta, but how do we actually implement this in the circuit? Well, as we saw when we were looking at some of the op-amp circuits and discrete circuits, we can relate this beta value to certain resistor values or other values in the circuit and use that to design this beta value. So what we're going to do is we want to first of all figure out what does it mean to have a phase margin of 45 degrees. Then we're going to figure out what frequency gives us that, and then we're going to find what beta is going to give us the appropriate magnitude at that frequency. So starting with our phase margin of 45 degrees. So we know that this is sort of in our desirable range, and again, having a phase margin of 45 degrees means that we're going to be able to adjust our system a little bit and it's still going to remain stable. So in terms of numbers, what does this mean? That means our phase, sort of our key frequency or our key phase that we are looking at our magnitude at is -180, and we're saying that the magnitude of this transfer function is going to be 1 when this phase is 45 degrees above that -180 degrees. So of course that's going to be a -135 degrees, and this is going to be when our magnitude of our loop gain function is equal to 1. Note if we're talking about in dB, then that's going to be the magnitude in dB is equal to 0. Okay, so now we sort of know what we want to go for. We want to have the magnitude of our loop gain equals 1 when our phase is equal to -135 degrees. So the next thing we want to figure out is what frequency causes our phase to be -135 degrees. And so we can see, again, we have a 3-pole system here, and we've got this in a convenient form so that we can easily see our 3 sort of corner frequencies. We notice in this case that they're relatively far apart, so we can use our linear Bode plot approximation to sort of get a general idea. If we wanted a more exact value, we could of course use some of the newer calculators or MATLAB or something like that to find an exact frequency that gives you this -135 degrees. So let's start by just considering the general behavior using our simple Bode plot approximation. So the general behavior of those 3 poles in the denominator. So first, let's say from that first pole, and let me use approximately just because we know, again, this is going to be approximation. We have it's going to be approximately -45 degrees when we're at that first corner frequency, which that first corner frequency was 10 to the third. Make that a little more legible. So coming up here, the first of the highlighted terms is our first corner frequency of 10 to the third. So we're saying at that frequency with our Bode plot approximation, we know that the phase is going to be roughly 45. We know if we go 10 times that, so if we increase that frequency and we say we go to 10 to the fourth, then we're going to have a corresponding phase that is going to be approximately -90 degrees. So our first pole is going to take us down to -90 degrees. Now our second pole, we know that at the second corner frequency, we're going to be at approximately -135 degrees. So that's for our second corner frequency, which is our second highlighted term above, which is 5 times 10 to the fourth. And so again, from our approximation, if we do 10 times that, so if we go to 5 times 10 to the fifth, then our phase is going to be approximately -180. And then finally, for our third pole, we go another 45 degrees down, so we'll be at approximately -225 for our third corner frequency, which was our third highlighted term up here of 10 to the sixth. And similarly, if we multiply that by 10, we have 10 to the seventh for our frequency, and that's going to correspond to our phase being approximately negative 270. Okay, so again, we can use this general Bode plot approximation because the poles are far apart. So let me just state that explicitly. So Bode plot, which uses the linear approximation, is okay because poles are far apart. If the poles were closer together, we would have to then go to finding a more exact way to calculate this. But of course, we said that we're looking for when the phase is equal to negative 135 up here. Well, of course, that sort of conveniently happens to be our second corner frequency. So let's look at using this corner frequency of 5 times 10 to the fourth is sort of our key frequency here. And sort of just to show how good that approximation is, let's write an equation for the phase angle of this transfer function, or this loop gain function rather. So let's come down here and we can say our phase in general is given by negative, and then we're going to have 3 inverse tangent terms being added together. And typically we would have f divided by 10 to the third plus inverse tangent of f divided by 5 times 10 to the fourth plus inverse tangent of keeping this general for now, f divided by 10 to the sixth. So this would be sort of our general equation for our phase angle. And so what we can do is we can then come in here and we can say, let's put in f equals 5 times 10 to the fourth, because up here we said that's approximately the frequency where we'll get our desired phase angle. So if we substitute this f in these 3 places here and we do these calculations, what we'll see is that this phase angle is equal to negative, and we have 88.9 plus 45 plus 2.86 degrees. So all these should be degrees. And so we get that this is approximately negative 136.76 degrees, which is about our negative 135. And so again, whether or not that's close enough depends on the actual, on the application that you're looking at. So notice I've written out the 3 terms in this second line here explicitly, just to show where our approximation is a little bit off. So we can see, for instance, that for this first term, we assumed that this would already be at its full contribution of negative 90, but it's still not quite there. At our second corner frequency, as we expect, that's having a negative 45 degree contribution. And then we can see here, we would have expected this contribution to be 0, but we actually are already getting a small contribution from that third pole as well. So that's why we get a slight difference. But let's go ahead and move forward saying, let's assume that this frequency is good enough. So now we know that that frequency is going to give us our phase of negative 135. So what we want to do now is we want to find the magnitude of our loop gain for this frequency. So find magnitude of our t of j omega for f equals 5 times 10 to the fourth. So our magnitude of that, and what we're going to do is we're going to say, let's set this magnitude, and so here we just have it as f. We're going to set that equal to 0, and not equal to 0, we're not dB. We're going to set it equal to 1, and then from that we're going to be able to solve for our beta. Okay, so we're saying that we want to set this magnitude equal to 1, so let me move this over here a little bit to give myself some more space. Oops, I accidentally caught that G as well, so let's do that. Okay. So if we go back to our general equation, we can get the magnitude by doing the square root of a squared plus the square root of square root of a squared plus b squared. And going back to our general form, we have 1 plus, and now the frequency we're plugging in is 5 times 10 to the fourth. And this first corner frequency was 10 to the third, so that quantity squared, square root of 1 plus, again, we have the 5 times 10 to the 4th is the frequency at which we're evaluating. Our second corner frequency was 5 times 10 to the 4th, so it's going to be another 1 squared. And then finally, we have 1 plus 5 times 10 to the 4th divided by our third quarter frequency, which was 10 to the 6th squared. And in the numerator then, our magnitude was just the beta times 1,000. Okay, so again, we're evaluating at that frequency of 5 times 10 to the 4th. So we get that our 1 is approximately equal to, and we're going to have our, of course, beta times 1,000, just sort of along for the ride at the moment. And our first term in the bottom is going to be the 50.01. We have 1.41. And we have 1.00. And so I've again just broken that down to show you how each of those 3 poles is contributing to this magnitude. And so at this point, of course, we can just solve for our beta, and we can see that our beta is going to be approximately 0.0708. So this is the beta value that would give us our 45-degree phase margin. And so again, as I said at the start of the video, keep in mind, how would we actually set this beta? Well, of course, the answer is it depends on the particular circuit, but by choosing appropriate resistor values, capacitor values, various things in the circuit, we can set this beta value. One other thing to note is that knowing this beta value, we can now find our closed loop gain of the system. So we can find our closed loop gain for this 3-pole amplifier. So our closed loop gain, or our gain with feedback, is equal to our open loop gain divided by 1 plus beta times our open loop gain. And so what we have then is our open loop gain is just going to be that 1,000. So we have 1,000 divided by 1 plus our beta, which we just found to be 0.0708 times 1,000. And evaluating that, we find that our open loop gain is approximately, our closed loop gain is approximately 13.9 for this system.